I see it. So our third speaker is Jenn Hu, currently at Harvard. Um,
Hey, awesome. So today I'll be talking about cognitive benchmarking of neural language models with a case study in Pragmatics. So if you're at this workshop, you probably agree that there is a problem with the status quo of AI evaluation or kind of standard approaches to benchmarking, right? So it's well known by now that models can achieve high performance in benchmarks without, actually grasping the kind of linguistic or cognitive competence that the benchmark is designed to evaluate. And one kind of recent response to this is to try to fix benchmarking, like creating adversarial examples or including humans in the loop or just throwing a bunch of tasks at the model. But even with these kind of proposed changes, a lot of the underlying goals and mechanics of benchmarking are still the same. So instead of talking about better benchmarks, today I might talk a little bit about a different way of framing the problem of model evaluation, which is inspired by questions and methods in cognitive science. So typically when people build a kind of traditional benchmark, they start by asking, like, what are the downstream tasks we want our model to do well on? So this might be like image classification or translation. Whereas a more cognitive approach is to ask first, what are the behavioral signatures of human-like linguistic knowledge? And what are the inputs and outputs that we expect from a system with a human-like language? So for example, we know that humans make fine-grained distinctions between sentences that satisfy the grammatical constraints of their language and sentences that don't. Another conceptual difference is that in many cases, benchmarks will provide training examples for models to kind of start to learn or fine tune on the task. And in a lot of the cognitively framed evaluations that my colleagues and I have been doing, we often evaluate the emergent capabilities of models trained in a more general objective that has some cognitive significance. So we might take an autoregressive language model and investigate what kind of information is implicitly learned through this general task of linguistic prediction. So in the rest of my talk today, I'm going to illustrate this approach through a case study on pragmatic inference. And I'm going to focus especially on the kind of methodological approach we took instead of just focusing on the results to hopefully give a better sense of how this kind of cognitive AI benchmarking can be applied in different linguistic domains. So first, let me briefly introduce the phenomenon that we're interested in. Let's say your friend says the dog ate some of the cookies. In a strictly literal or logical sense, there are two potential meanings that are compatible with this utterance. So one possibility is that the dog ate some but not all of the cookies, which is shown like in this left jar here. And the other possibility is that the dog ate all of the cookies. But as a listener, you're probably thinking that if the speaker had known that dog ate all the cookies, they would have used the word all instead of some. And so based on this unspoken alternative word all, you can draw a pragmatic inference and infer that the word some actually excludes the meaning of all in this context. And this general kind of inference pattern is known as scalar implicature, or SI. And importantly, this kind of inference arises based on a special relationship between the words some and all, where some and all convey information on the same kind of scale or dimension, but some is weaker or less informative than all. And this reasoning pattern we saw could apply to other scales or pairs of words that share this kind of relationship, like possible and certain, warm and hot, or like and love, and so on. So this is a signature example of how humans understand language beyond literal meanings. And so we want a way of measuring whether language models can capture these kinds of inference patterns. So first, I'll talk about a kind of classic or traditional benchmarking approach to this problem, which has been proposed to evaluate models' ability to make scalar inferences. And this approach is based on the NLP task of natural language inference. So for example, you would construct a premise sentence like Joe ate some of the cake, and a hypothesis sentence, Joe didn't eat all of the cake. And then these sentences are fed to a natural language inference model, and the model classifies the relationship between these two sentences as one of three potential options. And the important options here are either a neutral relationship or an entailment relationship. So a neutral relationship between the sentences kind of corresponds to a literal interpretation, since some and not all are literally compatible with each other, but they don't necessarily imply each other or contradict each other. And then under this kind of evaluation paradigm, an entailment relationship between the two sentences would correspond to a pragmatic interpretation or reflect a scalar implicature. So this approach has all the advantages of classic or traditional benchmarking. It's straightforward to define a sense of accuracy or a measure of how pragmatic a model is. There's also a large number of items or scales, which can test models' knowledge across many different words and semantics. But on the other hand, it's not clear this is actually measuring the human likeness of a model in a pragmatic sense. So this task of natural language inference or predicting this like neutral or entailment relationship is used because it's a standard task in NLP, but it's not clear that humans would actually label scalar implicators in this way. And this approach also implicitly assumes that the correct or the ground truth thing to do is to always predict this entailment relationship, which treats scalar implicators as this categorical, homogeneous thing that is in tension with the actual empirical literature in human behavior. It's also not clear what this approach can tell us about how humans make pragmatic inferences. And I want to emphasize this is not necessarily a fault of the benchmark, and it wasn't designed with this goal in mind, but an alternate approach could potentially yield complementary insights from both AI and cognitive perspectives. So now I'll walk through kind of the conceptual overview of our approach, which adopts some of the cognitive benchmarking concepts that I mentioned earlier. So our first step is to determine like behavioral signatures of what human-like scalar inference patterns actually looks like in a completely task-agnostic way. So to do this, we turn to a large body of experimental work in psycholinguistics, which shows that scalar implicature rates are highly dependent on the context and on the particular lexical items. And so a large body of work has shown that there's a lot of variation in these scalar inference rates, both within a single scale and across different scales. So let me just give you a sense of what variation within a scale looks like. And we're going to focus on the scale of sum and awe, which we talked about earlier. So in a large-scale human empirical study, it was shown that when humans see sentences like this, I like some country music and I like some but not all country music, they rated these two sentences as highly similar in meaning, which suggests that there is a very strong preference to draw a scalar inference here. But then if you show humans a pair of sentences like this, it would certainly help them to appreciate some of the things that we have here. And it would certainly help them to appreciate some, but not all of the things that we have here. They rate these sentences as not similar in meaning, suggesting that some and some, but not all aren't meaning the same thing in this context. And so there's a very low scalar inference rate here. There's also a lot of variation in these scalar inference rates across different scales. For example, the scale formed by the adjectives possible and certain, or ugly and hideous. So in a different set of experiments, it was shown that humans are highly likely to infer that success is possible implies success is not certain, but they were not likely to infer that the painting is ugly implies the painting is not hideous. So going back to kind of our first step in designing a way to evaluate models and scalar inference, the empirical phenomenon that we're actually interested in explaining or seeing if our models can capture is this fine-grained and systematic variation in scalar inference rates, both within and across scales. And then now that we've determined that, our next step is to design or choose a metric that measures how well models actually capture this empirical target or this phenomenon. So to do this, we're going to take inspiration from a cognitive hypothesis, which is that the strength of a scalar inference depends on how expected the unspoken alternative is. So in other words, the more expected or predictable the alternative is in the context, the more the speaker's choice not to say it suggests that they didn't have grounds to say it or they didn't believe it was true. So in other words, the more expected the alternative is, the more confident a listener should be in drawing a scalar inference. Now, the question is, how can we measure the expectedness of these unspoken alternatives? And to do this, we'll use language models as a way of estimating human linguistic expectations. So concretely, let's say a human sees a sentence like the food was fine, and we want to estimate how expected is the word delicious as an alternative to fine in this context. So what we do is we create these sentence constructions that set up expectations for kind of scalar contrast, like the food was fine, but not blank. And it's been shown before that humans will expect a kind of strong scalemate to appear in the position of that blank. And then we use language models to estimate these expectations. So we look at the distribution over possible words that could go in that blank. And in this case, if we're interested in the expectedness of an alternative like delicious, we just look at the probability of delicious assigned by the language model in this context. So more generally, going back to our prediction, Essentially, we're testing for a positive relationship between human scalar inference rates and the probability assigned by a language model to the unspoken alternative given this scalar construction context. And so going back to our general approach, since our goal is to capture variation in these human scalar implicature rates, the metric we're going to use to evaluate our models is the correlation between human scalar inference rates and these model probability values. So there's no notion of accuracy or the pragmaticness of a model. It's all about whether the model captures fine-grained patterns of these inference behaviors. So I'll go super quickly over the results and refer you to the paper for the details. But essentially, we tested our models on 5 empirical data sets, including like thousands of sentences and around 150 different unique scales. And we found that these model-derived probability estimates explain significant variance in human scalar inference rates across these data sets. So that's like these negative correlations that we see here. Again, I won't go over the details in the interest of time, but yeah, we found the predicted relationship for all but one of the tested data sets. From an AI perspective, this suggests that models can encode information that's relevant to these really fine-grained human pragmatic inference patterns. And from a cognitive perspective, it provides support for expectation-based theories of pragmatic language understanding. So now I'll just say some final thoughts. I think that cognitive evaluation can complement traditional AI benchmarking and provide new insights from AI and cognitive perspectives. But also, I think there are a lot of challenges for this enterprise going forward, which I think will be kind of useful, maybe a starting point for discussion. So one set of challenges is practical, right? As our models are getting bigger and the training data sets are getting more and more opaque, I think it's becoming more and more of a challenge in terms of designing stimuli that actually test generalization in large models, kind of as Tal was also alluding to in his talk. And also there's this practical issue of how we can create high quality data sets at large scales. We also have a set of important theoretical challenges. First of all, how do we even define or agree on the correct behavioral and representational measures of human likeness? And in the current landscape of AI and NLP research, there's so many evaluation methods like prompting or direct probability comparisons or representational probing, and a priori, all these methods could give different conclusions. So I think as a field, we need to develop like better norms and ways of trying to reconcile all those different potentially conflicting sources of information. And then finally, there are a lot of social challenges as well. So, I think it's definitely an open and relevant question about how we can foster more interaction between experts in AI and cognitive science, and what tools we could potentially build that will leverage the unique strengths of these different communities. So I am over time, so I'll just say thank you to collaborators on this work, which is coming out in Tackle this year, and thank you so much to the organizers for putting on this event. Thanks.